All right, so what we've sort of come through so far in our lectures is the brief introduction on how we're going to describe motion using position, velocity, acceleration, and time as our main sort of words and concepts we use to describe that motion, how to visualize motion with motion diagrams, and we also went through units and how they relate to our descriptions of motion, and significant figures and how we address those. Today, we're going to sort of walk through an example of how we can sort of put all this together and introduce a new sort of representation of motion as well. And we're going to work through essentially this example. So the example is you're on some unknown planet, planet X, and you throw a rock straight up and you measure the position of that rock at various times, and they're listed below. This is what you've measured. So if I wanted to draw a motion diagram for this, well, we should be getting very comfortable with that. That's where the rock started when I threw it. A second later, it's up at 17.5 meters. Then it's at 30. Then it's at 37.5. Then it's at 40. Then it comes back down. For motion diagrams where they turn around like this, one strategy is to, rather than drawing dots on the same line, draw the same dot that you did at the top at that turning point and just move it over. So that's the 40 meter point again. And then it starts to come down, 37.5, and then back to 30, right? So these are my positions, x0, x1, x2, x3, x4. Then I've drawn x4 again, just to give me some room, x5, and x6. And the values are all listed in that table. If I wanted to add some things, more things to detail to this motion diagram, the next thing would be there's my velocity vectors between each set of positions, turns around, starts coming back down. And if I wanted to go even one step further, we know how to draw the accelerations for those. Those arrows are getting smaller, so that acceleration is pointing down through those points. And we're hopefully pretty familiar with all this from the previous lectures and getting comfortable with now. We want to add a coordinate system, so that would be my origin. I've still been using the label X, so we'll call this the X direction going up, and that's sort of what we've got. We can see a lot of details of how this motion works just from that motion diagram. We've also slowly started to be able to calculate values for these. We did that a few videos ago. So if someone were to ask, what's the velocity of the ball on this planet, how would you answer that? Well, it's a pretty vague question, right? What do we mean? The velocity is clearly changing. You threw it up very fast, it slowed down, it turned around. What are we talking about? Well, we could calculate the velocity from 0 to 1 second, and we'd calculate that as just our change in position over change in time. And that would give us 17.5 meters minus 0 meters, all divided by that 1 second time change. And we get 17.5 meters per second. But we could also calculate, what's the velocity from 0 to 6 seconds? What's the velocity over that whole trip? And that would be the change in position over the change in time. And in this case, since the position after 6 seconds is 30 meters, and the position at 0 is 0, 30 over that, change in time would be 6 seconds, that would be 5 meters per second. You can look at this and you can say, well, which one's the right answer? And really, that's kind of the wrong way to think about it. These are both physical calculations that mean things, but they just mean different things. And the way we're calculating these velocities as change in position over change in time, what we're actually calculating is the average velocity over whatever time interval we're looking at. So right here, the first way we calculated the average velocity from 0 to 1 second, right? If we actually think about this, the velocity is changing even in that second, but within that second, but 17.5 meters per second is the average velocity in that time interval. Likewise, when we look at this one from 0 to 6 seconds, we're calculating the average velocity for the whole trip. So depending on the information you're looking for, either of these could be more appropriate to use, right? If we wanted to know how fast it was going at 4.5 seconds, we would calculate the velocity, from 4 to 5 seconds. Where'd that be go? Which would be the change in position over the change in time again. But this time it would be 37.5 meters minus 40 meters, all divided by that 1 second time interval, and that would equal negative 2.5 meters per second, right? Which clearly it's negative. It's going in the opposite direction as both of these previously calculated velocities. So if we wanted to know the velocity somewhere in this time interval, we'd want to use this because it would be more appropriate. But the main takeaway from this is the way we've been discussing how to calculate these velocities, and accelerations would be the same as well. What we're actually calculating is the average velocity over that time interval, delta t, right? So we're going to build on that and go from there and start looking at this problem with a little more detail and start to look at it graphically. So let's look at this graphically. All right, so we have the same set of data we took from throwing this rock up. Now we've calculated the average velocities as well for each 1 second time interval. So the average velocity from 0 to 1 second, 1 second to 2 second, and so forth. If we wanted to plot this graphically, how would we do this? Well, we have on the vertical axis, we have the height, which is our position, and we have time. So at 0 seconds, we're at 0 meters. So we have a data point there. After 1 second, we're up at 17.5, so somewhere like this. 2 seconds, we're up at 30. After 3 seconds, we're at 37.5, so somewhere here. After 4 seconds, we're at 40, somewhere here. After 5 seconds, we're at 37.5 again. And after 6 seconds, we're back down at 30. So that's what our data points look like, right? So we can plot the position as a function of time on a graph just by plotting those ordered pairs, sort of the position and the time values. The question is, what else can we read off this? Well, if we think about how we calculated our average velocities, let's look at the average velocity from 0 to 1 second. This was x1 minus x0 all over t1 minus t0. And if we look at what that is, so that's this x1 is this value here, and x0 is the 0 value. So that x1 minus x2 is this difference here. And if I look at the t1 minus t2, well, this was t1 at 1 second. This was t0. So this distance on that axis is my denominator. So what I'm actually calculating is the rise over run between these 2 points, or that velocity is the slope of the position versus time graph on between those 2 points. And if I go to the next velocity that we calculated, it's the same sort of thing, the rise over run. So as I'm going, the average velocity is the slope between those 2 points, is what we've been calculating. And that holds for any 2 points. If I wanted to get, if you recall from just a second ago when we calculated the velocity from the entire trip of 5 meters per second, what that was the slope. It's going to be harder to draw freehand, but the slope of the line connecting those 2 points. So this was v average from 0 to 6 seconds, whereas each one of these was, the slope was v average from, this one would be 1 to 2 seconds. So again, we can represent the same sort of motion now in a motion diagram, something sort of a visual representation. We've started to work on a mathematical representation of it where we can put some numbers to it. And now we've also added this graphical representation. And you can see, though, that these straight lines, well, as straight as I can draw them freehand, probably, if we were to have more data, they probably wouldn't be connected by a straight line. And it turns out, as we're going to build through these examples, we're in the next lecture, we're going to develop calculus and show that these average velocities, they're an average velocity over a given second in this case, but if we had more data points, if we had taken more data, we'd see that they're not the best representation for velocities at any instant within that interval. And calculus is what's going to take us to that next step, where we can calculate actual instantaneous velocities and instantaneous accelerations. And we'll build on that in the next lecture.